Let's look at an example here where we are asked to find the acute angle between the lines x plus 2y equals 7 and 5x minus y equals 2. We only have two variables, x and y, and these are described as lines. This means we're working only in R2, the xy plane. We will see later in this chapter how to describe lines in R3, the three-dimensional space. They're a little bit more complicated. But for right now, this is just a fairly straightforward sort of situation. We're in R2, we have these two lines given to us. To find the angle between them, we will need to know their slopes. And if you're comfortable reading slopes off of equations in standard form like this, just negative a over b, you can certainly do so. Many of you may find it easier to first rearrange these equations by solving for y. And it looks like the first equation would give us something like 7 halves minus 1/2 x, meaning that there our slope is negative 1/2. And for our second equation, solving that, that looks like we'll have a 5x minus 2. So that our second slope is equal to 5. So let's, I'll draw a rough sort of sketch here. We have a slope of negative 1/2. And I'm just kind of going to kind of eyeball things. Not a negative 1, but a negative 1/2. So, maybe somewhere around here, give or take, as our first line. And for the second one, a slope of 5. That is going to be quite steep. Not sure exactly how steep, but let's just do something sort of like this. So these lines intersect someplace. We don't actually care where in the plane they intersect. We just care about how they intersect, right? Now, knowing these slopes, we can come up with vectors that describe these directions, right? So this first slope, we have negative 1, negative 1/2, which we can think of as negative 1 over 2, or 2 over negative, or 1 over negative 2. So we can interpret this as either meaning that we go right 2 units and down 1 unit, or that we go left 2 units and up 1 unit, right? Either of those would give us this slope we're looking for. So that would imply that in this direction, we could draw a vector with components 2, negative 1. And in this direction, we could draw a vector with components negative 2, 1, right? Similarly, for this steeper line with a positive slope, we could interpret that as going right 1, up 5. So we could think of a vector that goes right 1, up 5 with those components. Or we could think of it going left 1, down 5. So this could be negative 1, negative 5. Now, looking at this, so we're asked to find the acute angle. And from my sketch, which is not very precise, so it could be wrong, but at least from the sketch, it looks like the acute angles are these, right? The other two look like they're obtuse. Now, between the 1, 5 and the negative 1, 5, I would rather have more positive numbers. So let's choose that vector as one of them. That came from the second equation, so I'll call that vector b. 1, 5. And we'll pull a vector a from the first equation. And since we're using this vector here, we want to find the acute angle, so let's take this one that goes negative 2, 1. Okay. So these directions can be represented as these vectors here, negative 2, 1, and 1, 5. And we're asked to find the angle between those. Well, we have theorem 3, which tells us that a dot b is equal to the magnitude of a times the magnitude of b times the cosine of the angle between them, which I'll call theta. So we have our vector A, which is negative 2, 1, dotted with our vector B, 1, 5. That will have to equal the length of A, so that'll be the square root of, I'll write this here, negative 2 squared plus 1 squared times the square root of 1 squared plus 5 squared times the cosine of theta. Now that I've copied everything, let's scroll this down to here, give us some space to work with. Evaluating the dot product, I'll write out every little step here since I think this is the first one of these I've worked through. In practice, of course, you would probably, once you become practiced with these things, you'd probably skip one or two of these intermediate steps that I have here. Remember, we multiply the first components and multiply the second components and add the results. And here we have the square root of 4 plus 1 times the square root of 1 plus 25 times the cosine of theta. So we have negative 2 plus 5 equals the square root of 5 times the square root of 26 times the cosine of theta. Negative 2 plus 5 is 3. 5 times 26, 260, 130. So this means that 3 divided by the square root of 130 is equal to the cosine of theta. And that implies that the angle theta itself, since we are looking just for the angles between these, we can just take the arc cosine. Depending on the kind of problem you're solving, remember that, a trigonometric equation like this has infinitely many solutions, and the inverse trig function does not always give you the one that you want. But in this case it will. The arc cosine gives us an angle between 0 and pi, or between 0 degrees and 180 degrees, and that's what we want here. So we can just say that theta is equal to the arc cosine of 3 divided by the square root of 130. And if you are doing something where it is asked, actually theta wasn't part of the thing, if you're doing something where it just asks you for an exact answer, that would be the solution. And this is the fully simplified exact answer for this problem. Again, if you want to rationalize the denominator, you can, but in this case, nothing's going to cancel, right? 3 is not a factor of 130. So it just makes things actually slightly messier if you do rationalize, but that would be acceptable as well if you prefer to do so. If you're doing a problem where you would like an approximate measure for that, looks like that works out to, if my notes here are accurate, about 74.7 degrees. So the approximate answer in degrees would be this. So let's see, 74.7, so about 75 degrees. That's that's not too bad. My picture kind of indicated that. Now, I drew the picture mainly to illustrate this point of how we can translate slopes into vectors, but we don't need a picture. You could just take each slope, translate it into a vector using the idea of, you take a rise over a run, a change in y over change in x. The change in y and change in x can just be translated directly into vector components. Like I said, each one you have two choices, but just pick whichever ones you feel like. If you happen to pick a pair that don't work, that don't quite give you the angle you're looking for. So for instance, for the slope of 5, you should write that as 1, 5. It would be kind of weird to choose the negative version. But for the slope of negative 1/2, it's not clear whether it would be best to have the negative 2, 1 or 2, negative 1. So you can pick whichever you want. If you were to choose this other one, most of the math would work fine. The only difference, you have signs in different locations. So in that case, you'd have a positive 2 and a negative 5, so you'd get a negative 3 here. So you would have gotten, as a result, the arc cosine of negative 3 over the square root of 130. And if you think about your cosines, you know that cosine is positive in the first quadrant, so this gives you an acute angle. Cosine is negative in the second quadrant, so this would tell you have that you have an obtuse angle. Since the problem asked us for the acute angle between the lines, you would then want to just say, oh, well, it's actually the positive one, right? So you can say this is obtuse, the positive angle would be, the acute angle would be given to us by this expression, and you can still write that. Maybe you weren't asked for an exact answer, so you're just going to use the calculator and approximate these things. Well, when you compute that, you would get 105.3 degrees. And hopefully when you look at that, you realize, oh wait, this is not acute, that's obtuse. We need to subtract that from 180 degrees to get the correct acute angle, which would be the 74.7 degrees. So this is a quick little example to show a few things. Firstly, how we can translate slopes into vectors. And if you think about that, of course, that also means you can turn vectors back into slopes. If you have a vector giving a direction and you need to describe a line that is parallel to that vector, well, the components of the vector tell you what slope the line needs to have. Also, some reminders of acute and obtuse angles and how the trigonometry works with that. And of course, the central point, which was illustrating an application of Theorem 3 here, one of the many things that we can do with this. Also illustrating what I meant by how I just use Theorem 3 and plug things in and solve for what I don't. It's, the only additional step that you have is, okay, well, you have to divide this thing to the other side, right? But that is hopefully not too difficult once it's simplified. If you do memorize something, one of the formulas for cosine theta, or theta itself has an arc cosine of like a dot b divided by the product of the magnitudes, like you can use that. That's fine. But it's just one extra formula. You can get it very easily from Theorem 3. Again, most of what I did here was computations you would have to do no matter which way you wrote this. But yeah, there's a nice little example of applying dot products in an analytic sense here.